Hello everyone, in this video I'll be explaining the chemical reactions of haloarenes. Now haloarenes, or they are also known as aryl halides. Haloarenes or aryl halides, they are extremely less reactive towards nucleophilic substitution reactions due to the following reason. Now if we check the reactivities of when we compare the nucleophilic substitution reaction of haloarenes, we will notice that haloarenes are extremely less reactive towards nucleophilic substitution reaction. Now the first condition is because of resonance effect. Now in haloarenes, the electron bear on the halogen atom. Now if this is our haloarene, there are 7 valence electrons in halogen atom. Now one electron is used in bonding, the other electron bears. Now there are 6 more electron bears. There are 6 electrons in our halogen atom. Now here, if we check out in haloarenes, the electron pair on the halogen atom are in conjugation with the pi electrons of the ring. Now because of this, there are some resonating structures possible for haloarenes. Now if this electron shifts here, this electron moves here, then we'll be getting our second resonating structure. Since this bond shifts here, a negative charge will be formed here, and then there will be doubly bond character between a halogen atom. This would acquire a positive charge. Now again, if this electron pair shifts, this one comes, then we'll be getting our third resonating structure. Electron. Now again, if this electron pair shifts here, this comes here, and then we'll be getting here a negative charge, X, positive charge. Now if this one goes here, this goes back, and then we'll be getting here our haloarene back with all its 6 electrons. Now if we check from these resonating structures, we can see that the electron pairs that is with the halogen atom, they are in conjugation with the pi electron ring of the ring, and thus the following resonating structures are possible. Now let's mark 1, 2, 3, 4, and 5. Now if we see here in our structure 2, 3, and 4, we will notice that the carbon, these are carbon to halogen atom. In all of these 3 structures, the carbon to halogen bond acquires a partial double bond character due to the resonance. As a result, the bond cleavage in haloarene is difficult than in the case of haloalkane, and therefore we will see that they are less reactive towards nucleophilic substitution reaction. Now the second condition here is because of the difference in hybridization, hybridization of the carbon atom in carbon to halogen bond. Now if we check the hybridization of the carbon atom in the carbon to halogen bond, we will see here that in our haloarenes, these are haloarene X. Let me write haloalkane here. Now here we will see here that in haloalkane, these are haloalkane, and this is our haloarene. In haloalkane, we will see here that the carbon atom attached to the halogen atom is our sp3 hybridized, while in the case of haloarene, this carbon atom is sp2 hybridized. Now the sp2 hybridized atom has a greater, this our sp2 hybridized, this is sp3. If we check the s character in sp2 hybridized carbon atom, in sp2 hybridized carbon atom, it has a greater s character. S character is more, the sp2 hybridized carbon atom with a greater s character is more electronegative and can hold the electron pair in the carbon to halogen bond more tightly than in our sp3 hybridized carbon atom. In haloalkane, having a lesser s character here. Now, thus the carbon to halogen bond line in our haloalkane is, in haloalkane, the carbon to halogen bond line is 177 picometer, while in haloarene it is only 169 picometer. Thus, since it is difficult to break, we know that it is much more difficult to break a shorter bond than a longer bond. Therefore, we will notice that haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. Now the third one is our instability. Now the third one is our instability of the phenyl cation. Now, in the case of haloarenes, when we see here, in the case of our haloarenes, the phenyl cation, as a result, this is our phenyl cation, as a result of self-ionization. The phenyl cation, as a result of self-ionization, it is not stabilized by resonance, whereas therefore there is no feasibility for SN1 reaction. Therefore, since in our haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is not possible in our haloarenes. Now the fourth one is our due to electronic repulsion. Due to electronic repulsion. Now, because of electronic repulsion, the approach of an electron-rich nucleophile towards electron, we know that our haloarenes are electron-rich species. Due to the approach of an electron-rich nucleophile towards our electron-rich haloarenes, it is not favored because of our electronic repulsion. Therefore, because of these following conditions, nucleophilic substitution, we will notice that haloarenes are much lesser reactive towards nucleophilic substitution reactions than haloalkanes. Now with that, let's check out some nucleophilic substitution reactions of haloarenes. Although they undergo nucleophilic substitution reaction, the reaction occurs only under drastic conditions for our haloarenes because they are less reactive than haloalkanes. The first one is our replacement by a hydroxyl group. Now, if nucleophilic substitution reactions were to occur in haloarenes, we will notice that in haloarenes, this is our haloarene, any haloarene, the halogen atom is attached to our benzene ring, so it cannot be easily displaced by any nucleophilic agent. Thus, we know that the haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. Now, the first one, if we check here, when our chlorobenzene, now if we take here an example here, if our chlorobenzene can be converted into phenol This can be converted into our phenol by heating in the presence of aqueous sodium hydroxide at the temperature of 623 Kelvin and 300 atmospheric pressure. We will be getting here our, on hydrolysis, we will be getting here our phenol. Now here, the reaction occurs only under drastic conditions. That the condition here is that it occurs at 623 Kelvin and 300 atmospheres. Now, the presence of other substituents also on the ring in haloarenes also affects the nucleophilic substitution reaction appreciably. Now, for example, the presence of electron withdrawing groups. Now we have, if our electron withdrawing groups such as NO2. NO2 is present in, that is substituted in our benzene ring at the ortho and para positions. At the ortho, these are ortho, meta, para, meta, ortho. At the ortho and para positions, if electron withdrawing groups are substituted at the ortho and para positions to the halogen atom, then it greatly activates the halogen atom for nucleophilic substitution reaction. Now let's check out the examples that has electron withdrawing groups such as NO2, the nitro group attached to our benzene ring. Now the first example here is our, if it is attached at the para position. Now, if our nitro group is attached at the para position, then we see the presence of these electron withdrawing groups NO2 at ortho and para positions increases the reactivity of our haloarenes. Now here, the same reaction, aqueous sodium hydroxide, NaOH at 443 Kelvin. Then we will be getting here our phenol, NO2. Now, if it is again substituted, more substituents are present here at the para as well as at the ortho position. It will activate the halogen atom attached to the benzene ring even more. Therefore, and then we'll be getting here NaOH occurs at a lesser temperature, 368 Kelvin. We'll be getting here, it activates the benzene ring more, and then NO2. Now, if again more substituents, if more nitro group is substituted in our benzene ring at the ortho and para positions, here the reaction occurs only on warming. OH. Now the effect of NO2, the effect of the presence of NO2 group on the reaction conditions for nucleophilic substitution reaction happens at, the first one when it is only at para position happens at 443 Kelvin. The second one when it is both at ortho and para position, it occurs at 368 Kelvin. And when it happens at all the three ortho and para positions, then only on warming the reaction, it becomes, the reaction happens rapidly. Now the presence of other rings, other electron withdrawing groups such as CN, COOH, these are all electron withdrawing groups. They will also activate the halogen atom on the benzene ring, and it will make the nucleophilic substitution reaction easier. Okay, however, we will notice that we will see here that the effect is pronounced for NO2 when our NO2 group is introduced at the ortho and the para positions. However, no effect on the reactivity of haloarenes is observed by the presence of an electron withdrawing groups at meta position. Now, if in case we have here a meta isomer, if the electron withdrawing group is introduced at the meta position, no reactivity will be observed, because now here in the resonating structures, if we check here, this is the para nitrochlorobenzene. This is our ortho nitrochlorobenzene. This is meta chloronitrobenzene. Now the resonating structures for all the three isomers is given here. Now here in para nitro, when it undergoes nucleophilic substitution reaction, we will notice here that in both our ortho and para isomers, we will notice that in the resonating structures for our in the resonating structures, we will see here that there is a let me draw the resonating structures. This is for our meta isomer. Now this is our meta isomer we have when it reacts with OH, a hydroxide ion, the first slow sleep. Now this causes the electron pair shifts, and then we'll be getting here our, let me open the structure. And negative charge would be here, our OH is attached here, Cl is here. Now the second resonating structure we can check here. If the electron pair shifts here, we'll be getting here, this one will move here, and then nitrogen atom. Now if this shifts, this goes back here, and then we'll be getting a third resonating structure here, that is Cl OH. Bond would be formed, the negative charge would be here, now these are the three resonating structures, and then if this goes back here, our chlorine atom will leave out because they are good leaving groups, and then we'll be getting here our NO2 is here, OH is here, electron pair, and then Cl minus. Now here in the resonating structure, when the electron withdrawing group is attached at meta position, we will see here that in the resonating structures the negative charge, in the case of meta-nitrobenzene, in these three resonating structures, we will see that none of the resonating structures bear a negative charge on the carbon atom. That means we are focused on this carbon atom. We are focused on this carbon atom. Here in structure 1, 2, and 3, we will see here that in the three resonating structures, none of the carbon atom has negative pair and negative charge on the carbon atom that is pairing our NO2 group. Therefore, the presence of nitro group at meta position does not stabilize the negative charge and has no effect on the reactivity, and thus there is no the presence of NO2 group on the meta position has no effect on the reactivity of our haloarenes. Whereas if we check the resonance of our haloarene suite that happens at the ortho and para positions, let me draw here for ortho isomer. Let's do for para position. Now chlorine atom here is here, our NO2 group is here. Now cause an attack here, electron pair shifts here. Now the resonating structures we will be getting here, Cl is here, OH is here, negative charge comes here, and then now because of this we have here Rn and O2. Now if this electron pair shifts, now this comes here to this carbon atom. Now here we'll be getting here Cl is here, OH is here, double bond, our NO2 is here, negative charge is on this carbon atom, electron pairs. Now if this negative goes, this comes, and then we'll be getting our third resonating structure. And then if this goes, the chlorine atom leaves, and then we'll be getting our product. This is the mechanism for the para isomer. Now here in the para isomer, in the second resonating structure, we will see here that there is a negative charge on the carbon atom that is attached with our nitro group, and the negative charge that appears at it appeared at the ortho and para positions with respect to the halogen atom. Here, the negative charge appeared at the para position with respect to our halogen atom. Thus, this carbon anion, this is our carbon anion, it is stabilized through resonance. Thus, the reactivity, the effect of electron withdrawing groups on our ortho and para isomer will be more profound, and thus the nitro group shows no effect when it is at meta position, because we will see we have seen that in the resonating structures when it happens for our meta isomer. In the meta isomer, we will see that there is no negative charge. The three resonating structures has no negative charge on the carbon atom attached to a nitro group. Thus, the presence of nitro group at meta position does not stabilize the negative charge, and hence no effect on the reactivity observed for the presence of nitro group at meta position. Therefore, that is the chemical reaction. That is the nucleophilic substitution reaction of our haloarenes. Now, the second chemical reactions of our haloarenes, that is our electrophilic substitution of haloarenes. Now, due to the presence of our electron-rich benzene or our aromatic ring, the haloarenes undergo electrophilic substitution reaction easily. Now, the halogen atom directs the incoming substituent to the ortho and para positions relative to the halogen atom. Now, if we have this is our haloarene. Now, electrophilic substitution, the halogen atom, it directs the incoming substituent or the nucleophile at the ortho and para positions with respect to our halogen atom. Now, one important here, due to the minus I effect, halogen atom deactivates the benzene ring. Due to the minus I effect of the halogen atom deactivates the benzene ring. As a result, the electrophilic substitution reaction of haloarenes occurs slowly and only under drastic conditions as compared to benzene. Now, in class 11, when we are studying hydrocarbons, we have noticed that benzene undergoes electrophilic substitution reaction easily, whereas in haloarenes, because of the minus I effect, the halogen atom deactivates our benzene ring. As a result, haloarenes occur electrophilic substitution reaction only under drastic conditions. Now, the ortho and para directing influence of the halogen atom can be easily. Now we can understand this if we have a resonating structure here. Now, halogen atom, the electron pair, we know that there are electron pair. If this comes, and then double bond, we have a negative charge here. Now, if this comes, this goes. The carbon to halogen atom acquires a partial positive charge. Now here, we see here that due to resonance, the electron density increases more at our, these are ortho, meta, para, with respect ortho. Now, due to resonance, we see here that the electron density increases more at our ortho position, and the para positions here. These are ortho position. We see here that electron density is more at ortho and para positions. Now, further, the halogen atom, because of its minus I effect, has some tendency to withdraw electrons from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene, and hence the electrophilic substitution reaction in haloarenes occurs slowly and require more drastic conditions as compared to benzene. Now, let's check the first electrophilic substitution reaction of haloarenes, that is halogenation. Now, we will be getting our products at ortho and para position, because from the resonating structures we have noticed that the electron density is more at ortho and para positions. Now, here, if we have here our halogenation reaction, chlorine is here, halogenation, Cl2 in the presence of anhydrous FeCl3, halogenation reaction happens, we'll be getting here Cl, one at the ortho position, one at the para position, and the other at the ortho position, because we know that electron density is more at ortho and para. This is our 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. These are 1, 4 dichlorobenzene. This is 1, 2 dichloro. We have 2 chlorine atoms here. Now here, remember, the major product will be always the para isomer because of the symmetry, and it fits better into the lattice. Because of its symmetry, the para isomer, the para product will always be the major product. This is a halogenation. Now the second one is nitration. Nitration reaction here is in the presence of HNO3 concentrated H2SO4. I'm not explaining the mechanism because I believe that you have learned the mechanism of electrophilic substitution reaction of benzene in class 11. It is the same mechanism here, one at the nitro position and then one at the ortho para position. But remember, the para isomer, the para product will always be the major product because of its symmetry. Now, third one is our sulfonation. Sulfonation. We have here our chlorobenzene. This is our 1 chloro 2 nitrobenzene. This is 1 2 3 4 5 6. This is 1 chloro 2 nitrobenzene, and then this is 1 chloro 4 nitrobenzene, the major product. Here, sulfonation occurs in the presence of concentrated H2SO4. We'll be getting here 1 at the ortho position, SO3H plus, and 1 at the para position, SO3H. This will also here will be the major product. This is our here 1 2 3 4 5 6. Here the numbering here, this will get the first number 1 2 3 4 5 6. Now here, this is our 2 chloro. This is 2 chloro benzene sulfonic acid, 2 chloro benzene sulfonic acid, and this is our 4 chloro benzene sulfonic acid. This will also be the major product. Major product will always be the one predominating. Now we have the last electrophilic substitution reaction of haloarenes, that is our Friedel-Crafts reaction. Friedel-Crafts reaction. Now in Friedel-Crafts reaction, we will see here that the first Friedel-Crafts reaction, Cl in the alkylation reaction, C alkyl chloride in the presence of anhydrous AlCl3. Here also we'll be getting 1 para product and then 1 ortho product, CH3. Friedel-Crafts alkyl addition of an alkyl group into the benzene ring, Cl CH3. Here numbering here will be 1 2 3 4 5 and 6. This will be 1 chloro 2 methyl benzene, 1 chloro 2 methyl benzene. Here is 1 2 3 4 5 6. This is 1 chloro 4 methyl benzene. This will also be the major product here in Friedel-Crafts alkylation reaction. Now if we see Friedel-Crafts acylation reaction, addition of acyl group to the benzene ring. Here let's take an acyl, CH3 C double bond O Cl in the presence of anhydrous AlCl3. Now here we will also 1 Cl, addition of acyl group C double bond O Cl group to the benzene ring at the ortho and the para position. Here this will be here, this will get the first numbering 1 2 3 4 5 6. Here will be 1 2 3 4 5 and 6. The name here will be 4 chloro acetophenone. This is acetophenone group, 4-chloroacetophenone, and this is 2-chloroacetophenone. Here, this also be the major product. In all of the electrophilic substitution reaction of haloarenes, the major product will always be the para isomer, the para product. Now we will see here that the third one is our haloarenes also reacts with metals, reaction with metals. Now when it reacts with sodium metal, it is known as phytic reaction. When it reacts with sodium metal. Now haloarenes when it reacts with our haloarene, let me take chlorobenzene. When it is heated with sodium metal in the presence of triether, the halogen atom of the haloarene is replaced by an aryl group. For example, if we take here, we have here our 2Na. If we take 2 moles of chlorobenzene here, we'll be getting here our dibiphenyl. We'll be getting here, this is known as our diphenyl. This is known as our phytic reaction. That means when our chiral halides, they give analogous compounds when it is treated with sodium in the presence of triether. This is known as our phytic reaction with 2 moles of NaCl. Now the second one, it is known as Wurtz phytic reaction. Wurtz phytic reaction is that when a haloarene is heated with a haloalkane. Now here it is, when a haloarene, let me take chlorobenzene, is heated with a haloalkane. When a haloarene is heated with a haloalkane in sodium Na, let me take CH3Cl, chloromethane. This is chlorobenzene. This is chloromethane. It is heated with sodium in the presence of triether. The halogen atom, this halogen atom in both the haloalkane and halohydrine is replaced by, and the halogen atom on the haloarene is replaced by an alkyl group. Therefore, that is known as our Wurtz phytic reaction. Therefore, we'll be getting here, the product here is halogen atom is replaced by this CH3 group, CH3, and then we'll be getting 2 moles of NaCl. This is known as DOULUE, toluene. Now, this is known as our Wurtz phytic reaction. The difference here is that in phytic reaction, we are using 2 moles of haloarene, whereas in Wurtz phytic reaction, we are using a haloarene as well as a haloalkane in the presence of sodium, both in the presence of sodium triether. Here we are getting here diphenyl, here we are getting here toluene. When the halogen atom is replaced by the alkyl group from that of our chloromethane. Therefore, with this, I'm ending our unit 10, the unit of our haloalkanes and haloarenes.